having seen what Cartesian products of two sets are, let us now see some properties of Cartesian products. If you take the Cartesian product of the empty set with any set in any of these two forms, then the result is the empty set. And the second one says that if we have three sets A, B and C, then A Cartesian product B union C equals A Cartesian product B union A Cartesian product C. So it's like distributive law, except now instead of union and intersection, we have union and Cartesian product. A similar one is there where you interchange union and Cartesian product. It gives you A union B. Sometimes we say B cross C, okay? So that is equal to A union B cross A union C. So to prove these properties, let us go through the proofs and see. We will see that unlike the previous operations, Cartesian products have that unique thing where the elements are ordered pairs, not just any elements. For example, whenever you have a Cartesian product like this and you take an element in this Cartesian product, then that element by definition is of this form x comma y, where x belongs to A and y belongs to B. Okay, so unlike any set, for example, if we have a set C and we take an element C in this, then we don't really know anything else about this small c, right? For example, we don't know whether C is of this form or not. The only thing we know is that C is an element of the set capital C. That's what we know. But when we are given a Cartesian product, then in it all the elements are ordered pairs. At least in this type of Cartesian product. There are other types of Cartesian products also where more than two sets are involved, and the same thing is true for unions, intersections and all those things. But we will come across those things later on. Okay. Right now we want to study the operations on two sets, not more than two sets. Okay, so we want to prove these properties. For the first one, what we do, you see, by definition, if we just simply try to apply the definition in this case, what it says is that it is the set of all ordered pairs x comma y such that x belongs to the first set and y belongs to the second set. Right? Now, whether this is true, I mean, this is a conjunction. A statement x belongs to the empty set and another statement y belongs to A. It's a conjunction of these two statements. This obviously is always false for no object x can we have this. This is always false. And since this is false, the conjunction is false, which means that no ordered pair satisfies this condition. That means there is no ordered pair. In other words, this is just the nothing but the empty set. Because no ordered pair can possibly be in this set, for an ordered pair to be in this set, its coordinates, the first coordinate and the second coordinate, they should satisfy these conditions. The first coordinate can never belong to the empty set. So that's why this set remains empty. That's why it is equal to the empty set. In the same vein, we also have this. Okay, so that is just the first one, for which we need not go through the principle of extensionality of sets. I mean, from the definition itself, it follows immediately. However, for these ones, these two, we have to go in the usual way. So what shall we do? For the second one, for the first one of the second one, as usual, we have to show that this is a subset of this and this is a subset of this. So let x, okay. Now see, that's why I told you that while considering an element in a Cartesian product, you have the liberty of taking that element as an ordered pair. So instead of just taking x, we choose an element x comma y belonging to A cross B union C. Because after all, this is also a Cartesian product. So any element in this set will look like this. It is an ordered pair after all. And this implies, by definition, the first coordinate belongs to the first set and the second coordinate belongs to the second set. So this implies x belongs to A and it's not x. Y belongs to B union C, which implies x belongs to A, and since we have union, we can write this like this, or y belongs to C. Okay. Now, this implies x belongs to A and y belongs to B, or x belongs to A and y belongs to C. Why? Here we are applying the one of the distributive laws that we have in mathematical logic, which is just this: P and Q or R. For three statements P, Q and R, this is equivalent to P and Q or P and R. From this equivalence, we have used this implication, 1/2 of the equivalence. That's how we get this one. And now it's easy. X belongs to A and y belongs to Q. See, keep one thing in mind. Now x belongs to A and y belongs to B. Okay, not x belongs to B. So this and will not give you intersection. You have two different types of elements. So rather this will give you the fact that the ordered pair x comma y belongs to A cross B. Similarly, we have OR, ordered pair x comma y belongs to A cross C. Okay, and now we have the same element, ordered pair x comma y belongs to A cross B, or that same element belongs to A cross C. That's why now we will have union because we have OR. So this will imply from here we can write this will imply x comma y belongs to A cross B union A cross C. Now, as I have already told you, we can go back. Okay, instead of again taking another element, for example, u comma v belonging to this set and showing that that ordered pair belongs to this set, we can go back from here, but keeping in mind that whatever we are doing is logically correct, logically sound. So we can now start from here, start from the end point. Suppose I have assumed that x and y, x comma y, this ordered pair belongs to this, which means what? This is an element in a union of two sets. Forget for a moment that these two sets are Cartesian products. This is just some sets, some set, and this is some other set. So this implies, now we go in this direction, x comma y belongs to the first set or x comma y belongs to the second set. This is just simply the definition of union, right? So from here we get this. Then again we write this at length. X comma y belongs to A cross B means x belongs to A and y belongs to B. This comes from the definition of the Cartesian product. Similarly, this means this, or is already there. So x belongs to A and y belongs to C. So that means this implies this. So that's why we have written this. Then again, from here we can write this. Why? Now we are using this side of the equivalence. This also implies this. So we have been able to write this implies this. This implies this. And then you go like that using the definition of union and Cartesian product once more, you get this. So what have we achieved here? We have shown that any element in this set is again in this set, and at the same time any element in this set is again in this set, which just tells you that A cross B union C is a subset of A cross B union A cross C, and A cross B union A cross C is a subset of A cross B union C. From these two containments we get equality. We get this. A cross B union C is equal to A cross B union A cross C. Right? Now, so this is one of the distributive laws. The other one can also be proved similarly. Cartesian product doesn't have many general properties, but these are some of the properties, which are also not some major result, just some properties. Okay. Okay, now from this, okay, so how many operations have we encountered so far? We have seen what union of two sets is, what intersection is, what difference of two sets is, and now we have Cartesian product. Okay, these are the four basic operations which will frequently occur when you study mathematics. Anywhere you look at mathematics, you will come across these operations quite frequently wherever there are sets, and sets are everywhere. Sets and the theory of functions, they are the language of mathematics. Okay, mathematics can be expressed in this language. Any part of mathematics, the parts we have encountered so far, they are in a very convenient way expressible using sets and functions. Functions we have not encountered yet, but we will see that. Now, apart from these these four basic operations, there are some other operations also. One among them I will show, which is not that important, but sometimes it arises. It is called symmetric difference of two sets. For sets A and B, their symmetric difference A delta B. This is the Greek capital delta. Okay, just like we have English alphabet, we have Greek alphabets. So in Greek, this is capital delta and this is small delta. Since Greeks have investigated many parts of mathematics as well as sciences, so to honor them, we frequently use Greek alphabets. So A delta B, now this is again a set, just like the other operations. This operation will also give you a set, and that set is this: A minus B union B minus A. This is the symmetric difference, and now you can see why it's called symmetric difference. It has both the differences available for two sets A and B. We have A minus B and B minus A. Their union is called the symmetric difference of A and B. In terms of Venn diagram, we can try to see what the set is. Suppose this is A and this is B. So A minus B is this part, and B minus A is this part. So this is A delta B, this much. The region with horizontal lines, this is A delta B. Okay. Now from this Venn diagram, can you guess something about this symmetric difference? What I am asking is, can you see this set in a different manner? If I write this is also equal to A union B minus A intersection B, am I right? You see, A union B is this whole set, I mean both the interiors of the circles or the regions, both of them taken together. From that, if I subtract this much, A intersection B, then I am left with this much. So it should be like that. Although this is not a proof, it's just a speculation or a guess or a hunch, a conjecture. So we immediately see one potential result about symmetric difference. So let us just try to prove this, okay? So this equality we have to prove. This is equal to this. Remember, symmetric difference means this. We have to prove that that set is also equal to this. So again we have to follow the usual way. We show that this is a subset of this and this is a subset of this. So we start by taking an element here. Now see, here we don't have any Cartesian product or anything. So here we start by taking just simply an element. X belongs to A minus B union B minus A. And we keep on using the definitions to write it in a simple manner. So X belongs to the union of two sets. One set is A minus B, the other set is B minus A. So this means X belongs to A minus B or X belongs to B minus A. Always keeping in mind that this OR is inclusive OR, which means that X may belong to both the sets also. Now applying the definition of difference, this means X belongs to A and X does not belong to B. Recall the definition of difference of two sets. A minus B is the set of those elements that are in A and not in B at the same time. Or here it's just the opposite. X belongs to B and X does not belong to A. Okay, so unlike our previous situations or the previous proofs, here this structure or this statement does not immediately fall into one of the forms that we have encountered while studying the laws of mathematical logic. It is not like P and Q or R, because it has four simple statements: P, Q, R, S. So, but still we can apply that same distributive law, although in a more complicated manner. Let us see what I mean by that. Now I am continuing from here. Okay, this implies I can consider this itself as a statement: P, Q, R. Then I can apply my distributive law in the usual way. So that means my P is this whole statement: X belongs to A and X does not belong to B. P or Q and R implies P or Q and P or R. So this is P or Q, X belongs to B. And let me write and here. And P or R, X belongs to A and X does not belong to B. This is P or R. R is this one. X does not belong to A. Okay. Now, this is a disjunction. P or Q. That can also be written as Q or P, right? Because disjunction and conjunction are both commutative. So I write Q first. X belongs to B, or then I write this one. X belongs to A and X does not belong to B. Don't forget the brackets, okay? They keep track of the things. Without the brackets, we will immediately get confused. Similarly, we do here. P or R is the same as R or P. So X does not belong to A, or X belongs to A and X does not belong to B. Now we have that ready-made form for applying the distributive law here, because we have three statements. One statement or another statement and another statement. So it will be somewhat big, but we have to push through the things without getting afraid of the things, without getting afraid of how the things look. Okay. One thing at a time. When I am applying the distributive law here, I am forgetting everything else. To me, now the only thing in front of me is this, P or Q and R, which implies P or Q and P or R. That means X belongs to B or X belongs to A, and X belongs to B or X does not belong to B. That and outside is still there. Again we apply the distributive law. X does not belong to A or X belongs to A, and X does not belong to A and or X does not belong to B. Okay, now we have to make sense of these statements. What can we use in place of them, or we can replace them by what? So this implies, again I am writing from here, X belongs to B or X belongs to A. This is just X belongs to B union A, which I can also write as A union B, but let's be strictly logical for the time being. I mean, later we can be somewhat sketchy and slack, but right now let's just keep the orders intact. We first write B and then A. Of course, this is nothing but A union B, but we choose to keep everything in track properly. Okay, and X belongs to B or X does not belong to B. Okay, now this means actually what? You see, in any discussion of set theory, I have already told many times that there is a universal set. It is assumed that there is a universal set of which every element is an element and every set is a subset. So that means X belongs to B or X does not belong to B, which means what? X belongs to B union B complement. You see here, B, X belongs to B or X does not belong to B means what? X belongs to complement of B with respect to that universal set. But since the universal set is fixed in a given discussion, so B complement is well defined. We don't even have to mention that there is a universal set U. It is understood whenever we are writing B prime, that means the complement of B in a given universal set. Okay. So we get this. And similarly, here also x belongs to A prime union, we have OR, so union. And okay, now what about this? X does not belong to A or X does not belong to B. Okay, without thinking much, you just simply write what this means. X does not belong to A means X belongs to the complement of A. So X belongs to A prime. Or, okay, or X belongs to B prime. So instead of writing that once more, because we have or, I write this. A prime union B prime. Okay, now what does this imply? X belongs to, now in place of B union A, I can write A union B. And okay, now if you remember the properties that we have come across while studying different subsets, complement subset, etc., this is nothing but the universal set. Okay, any set and its complement, if you unite them, any set and the part that is not in the set, that means everything. So this is nothing but U. U is the universal set. And similarly here also, this is U. And okay, now here you see, looking at this form, this union, do you remember anything? It looks like it has appeared somewhere in some law previously. One of the De Morgan's laws, which says that A intersection B complement is equal to A complement union B complement. This law. So in place of A complement union B complement, we can write this A intersection B complement. And that we do now. And X belongs to A intersection B complement. So this is the other part. Now this implies, since we have X belongs to A union B and X belongs to U, that means X belongs to their intersection. So X belongs to A union B intersection U, and X belongs to U intersection A intersection B complement. Okay. Now, see, the universal set has the property that any set is one of its subsets. In particular, A union B is also a subset of U, which means that this is U, this is U, this is A union B. That means if I am taking intersection, that is the elements which are common to both A union B and U, that is A union B itself, because that is common, or you can use one of the previous laws that we have proved, which says that A intersection B is equal to A if and only if A is a subset of B. In this case, our A is this much, which is a subset of U. We already know because U is the universal set. That means here we have A union B and here we have U. So their intersection will give me the smaller set, the subset, which is A union B. So X belongs to A union P, and again same thing here, whatever argument we have carried out with A union B, now we are replacing that by A intersection B complement. That is also a subset of U, because after all it's also a set, so it will be a subset of the